start our 11th edition. We started almost. We were traveling a lot with, and we decided to make some what we have learned as we so we did these lectures, and then the next year we did lectures again, and now we are in the 11th. So our first speaker is Damian Galante from college, right? London, and he will speak about finite size boundary in gravity. So, all right. Thank you very much. Good morning, everyone. It's very nice to be here again. It seems I'm coming back more and more often, so that's great. For those of you that do not know me, I did my undergrad thesis here, working with Martin, that I don't know where he is, if he is around. And then I went on to do my PhD with Alex Buchel, who turned out to be Philip's student. So this really feels like being family, academic family school, which is great. And today I'm gonna talk about some topic that is it's kind of interesting. It's about general relativity. It's very simple, so it's very nice because it's easy to give in a student school. You don't need much more background than your master's general relativity course or your undergrad general relativity. And it's about trying to understand what happens to the theory of general relativity when we are in the presence of manifolds that have a finite boundary. This boundary might be time-like, or we might be in the weird Euclidean case where we just have spatial manifolds, and we would like to understand what happens to the Einstein equation and the theory of general relativity itself in that context. It seems like kind of, at the same time, it's a foundational topic, but at the same time, it's a little bit of a strange topic. People working on general relativity don't usually care about finite time-like boundaries. When I told Alex, actually at Perimeter, that I was interested in this topic, he was like, why are you doing this? Like, what's this boundary? And I was very excited, but we don't know how to formulate the theory of general relativity in the presence of this boundary. There seem to be new theorems about this, like regarding PDEs and stuff, very interesting mathematical stuff. And he was like, yeah, but what's that? What's this boundary? Where is this thing? So I'll try to make sense of this idea, and so that I don't sound like a complete crazy person from the get-go. I'd like to motivate this a little bit more. I'll try to tell you that at least in our theoretical physics community, this is something we got used to do in one way or another, and it's kind of time to push this boundary a little bit inwards and a little bit more finite, and try to say something concrete about this problem. Okay, so feel free to interrupt at any point. This doesn't have an end, so I can keep talking forever, but just interrupt and ask. Okay, and yeah, there are no good references for this, so you can start by reading Wald, and then they will have a short chapter on boundaries and how to change the action in order to insert a boundary, but it's still pretty much under development. So I'll try to share, at least, this is not my field of expertise, but this is what I learned from mathematicians working in general relativity in the last 2 years or so. I'll try to sound as mathematical as I can, but I'm a physicist, so okay, you should see all whenever I write theorem on the board, it's just physicist theorem. Okay. So boundaries, I already said, boundaries, where is the boundary? No boundaries. The general law in general relativity is that there are no local gauge invariant observables. And so what do we do? And I was trying to say before is that we use boundaries, in theoretical physics in a variety of contexts. I guess here you are more used to the case where the cosmological constant is negative, and then the asymptotics of space-time are already time-like. This is my Penrose diagram of ADS. This is the conformal boundary, so this is an asymptotically ADS space, and this is the boundary. The boundary is time-like, but it's very far away, even though light rays can go in finite time, bounce back, and come into the bulk. And in the last, I guess 30 years, we've been used to using this as a lab to understand strongly coupled CFTs, etc. And if you have done a calculation here, you very soon will realize that whenever you do some boundary computation, because the volume of the boundary is infinite, you will start seeing divergences. And then how we solve those are just by making a cylinder that is a little bit smaller in this Penrose diagram. It's still infinitesimally close to infinity. And this is what it goes under the name of holographic renormalization. So in a way that renormalization, that I guess it will become clear, it's a little bit weird. We learn how to push a little bit the boundary inside and do our computations and match them to CFT observables. So that's the first one. I guess historically, the case where boundaries were first inserted were in asymptotically flat spaces when we were trying to understand black holes and black hole thermodynamics. This goes back to the work by York that will appear multiple times in these lectures. And in that case, the Penrose diagram of my, say, evaporating Schwarzschild black hole will look something like this. People were trying to study thermodynamics of this object using the Euclidean path integral. That is something we will discuss later. But the observation made in that context is that if you compute the specific heat of this black hole, you will realize that the specific heat was negative. So at least thermally, this Schwarzschild flat black hole was unstable, and that was problematic in trying to understand its thermal properties. Okay, and this was a a Euclidean manifestation of the Lorentzian fact that the black hole is evaporating. And so there will be some interplay during the lectures between Lorentzian and Euclidean signature, which I still think deserves further development. But in this case, I guess the justification of having this negative specific heat was the fact that we know that this black hole was evaporating, and we don't really have a thermally stable cavity of space. Okay, and then York decided to do something, again, a little bit strange. And he considered the case in which now, instead of going all the way to infinity, we have the same black hole, the same Penrose diagram. But now he decided to cut the space somewhere before infinity. So he forgot about this region of space-time, and he considered now this cavity that I am, again, plotting in Lorentzian signature, but I'm talking about Euclidean results. And what he showed is that whenever you insert a finite boundary away from infinity, there will always exist a black hole, a large black hole that has a positive specific heat and thus becomes thermally stable. Okay, and this is even in flat space. I'm not talking about Hawking page or anything like that, ADS black holes. This is a Schwarzschild black hole in flat space in the presence of a finite boundary where I put some boundary conditions that will be the topic of discussion of most of the lectures. In this case, they are Dirichlet boundary conditions. I fixed the induced metric on this boundary. And then kind of magically, the black hole becomes thermally stable. In the case of black holes in ADS, if you study that, we believe that there are these solutions, these eternal black hole solutions that exist forever. And kind of the idea, or the Lorentzian idea, is that the Hawking radiation becomes in thermal equilibrium with the black hole itself, and then that thing becomes thermally stable.
For the order of logic,
yes.
You're saying that you're quoting Euclidean results. So suppose I want to do a computation. I will do a Euclidean computation. I will do a Euclidean computation that I know I can interpret that as a specific hit. And then after I find out, for example, that C is less than 0. Then I can draw that Penrose diagram, and then I know that the Penrose diagram goes beyond.
Yeah, I mean, yeah, these two things are completely independent in a sense, right?
No, because in the upper one, the spacetime keeps on going after.
Well, because I'm saying that this will evaporate, right?
But you know that because C is less than 0.
No, I know this because Hawking did some calculation and found Hawking radiation in a Lorentzian setting.
Because then when C is positive, you didn't draw that.
No, because this one actually I don't know the Lorentzian analog, and that's part of my lecture of tomorrow. I will try to do the Lorentzian dynamics of these boxes and try to learn a little bit from the Lorentzian result.
But in the second one, the idea is that the black hole won't evaporate because it will swallow its own radiation, right?
Exactly. Yeah. So like in ADS, the radiation has time to go all the way to the boundary and come back, and so that it stays in thermal equilibrium. Philip has.
So the stable black hole, its mass is comparable to the radius at which you put the boundary. The size of the box.
Yes, I will do the calculation in detail afterwards, but yeah, very much similar to the case of ADS. When you put a Dirichlet boundary in flat space, there will be two solutions that satisfy your boundary conditions, where you fix the thermal size to be beta and the size of the two sphere to be whatever r. There will be a large black hole and a small black hole, and the one that is thermally stable is the large black hole that has. Yeah. Okay. Other questions?
Maybe it was in the last part of your comment. So this reversion in the sign of the specific depends on the boundary conditions you
Yes. All this depends on the boundary conditions, and in fact, even to do this computation, you need to compute the specific heat. You will do something where you compute something like this thing of beta f, or maybe I'm missing signs. But in order to define this beta, you need boundary conditions. So I will talk about the Euclidean setup soon. This is supposed to be just words to get you excited, but I see that you already are, so that's great.
So there is no continuous limit between the lower and upper.
So there are two branches of black holes, the small one and the large one, and what happens is that in the limit where you take the boundary to infinity, the two collide with each other, and then it becomes the unstable black hole.
Does C becomes 0?
No, C becomes negative.
No, but first it was positive, so perhaps at a certain point it becomes 0.
But there is also a small black hole with negative specific.
Yeah. There are two black holes. Well, yeah, there might be a point where C is 0. I don't know what that means. But, yeah. All right. More? Okay, and the case I like the most, and why I came interested in this topic, is of course lambda positive. And I say of course, but maybe I shouldn't. So in a lambda positive universe, geometries become asymptotically de Sitter-like. So this is the Penrose diagram of de Sitter. The metric inside this patch is the static patch metric of de Sitter that can be written in this way. I guess many people here are familiar with this metric, but it's anyways good to rewrite it. And the interesting thing here is that if so this metric describes this patch over here that is called the static patch. Here, this is r equals to 0, where the true sphere reduces to just a point. So we think of this as the place where an inertial observer is sitting in this sphere. Globally, the topology is just the sphere times time. The sphere is growing exponentially, so we can think of a person just sitting in that sphere that is expanding exponentially in time, and because of this exponential expansion, effectively the speed of light is reducing, and so this observer is just stuck in this cavity that is the static patch surrounded by a cosmological horizon. So this is r equals to L, the cosmological horizon, and in this region of space, there's no asymptotically large region anywhere. So the only place where space-time grows infinitely large is this space-like surface that sometimes we call scribe. But there's no asymptotically large time-like surface like here in ADS, where we can anchor in a gauge invariant way our points, observables, etc. So there's a question even at the classical level of what are reasonable observables inside this little piece of space. And then, okay, yeah. Because in order to define gauge invariant observables in gravity, we need a place where we can kind of decouple all the gravitational interaction. And for that, the usual thing we do is to go arbitrarily far away. And that's where we compute usually charges, etc. Both in asymptotically flat and in ADS. We like to put anchor our points here, because here we know what we mean by points. And so we don't have that in DS. And so one might be tempted to follow York and also put some boundary inside the static patch. And consider the region in between the boundary and the horizon, or the region between the boundary and the worldline observer. And this, if you are following the archive, there are lots of developments now regarding Euclidean computations of this static patch that becomes the sphere, and how to interpret the partition function, the inclusion of observers, etc., etc. So it seems that in order to make sense of this piece of space, we need some kind of feature, either being a boundary, an observer, or something to be able to anchor our coordinates and do physically meaningful computations. Okay? So this is my maybe 10 minutes motivation. It looks like it's a lambda agnostic formulation of GR. And okay, yeah, and it connects to many different ideas that people have been discussing. I don't know whether I should keep going, but I will just list here some other places where these boundaries in one way or another played a role. One of those was the membrane paradigm. So at some point in the, I guess, the 70s or 80s, people were trying to isolate the physics of an event horizon. So they were looking at the Einstein's equations very close to there, and they were finding that by putting, so the horizon is a null surface, it's a little bit degenerate, so in order to make sense of that, they would push the horizon a little bit inwards and consider a time-like surface that is parametrically close to the horizon, and that's what people were calling the membrane paradigm. And by looking at the Einstein's equations in there, they realized that the Einstein's equations look pretty much like a fluid equation, and they were trying to characterize the gravitational behavior by looking at fluids in this context. This is work by Damour, Price, Thorne, and many other people since then. There is also this idea of trying to understand the black hole entropy as entanglement, and there the idea by Toft and many other people was to put some kind of brick wall close to the horizon where they were basically cutting the spectrum of quantum fields in a black hole background by introducing some hard cutoff. And I guess these ideas will start coming back very soon. Then with ADS-CFT, boundaries started appearing over and over, but maybe most relevant for us will be something that goes under the name of the holographic RG flow. People were thinking of the radial coordinate of ADS as some kind of energy scale, and so people were thinking of putting or taking the boundary inwards as computing some kind of RG flow in the boundary CFT. Lately, that was kind of revisited in a slightly different context in the CFT by studying these TT bar deformations, at least in 2 dimensions. And the last one that I liked a lot, and I thought a long time about talking about this in these lectures, is the near ADS2 story. So when we study near extremal black holes, we end up in this theory that is a 2-dimensional theory that we call the JT gravity, that has a 2-dimensional metric and a dilaton, and this dilaton is computing the size of the S2. And so looking at this theory from a higher dimensional perspective, having a large constant or nearly constant dilaton means that we are just putting a large boundary of finite size in my higher dimensional black hole. And so then we go into the throat, and the volume is infinite because we have this ADS2 throat. But at least from the boundary perspective, we are just cutting our space in a finite 2-dimensional large ball. So again, the problem of boundary conditions will start appearing over and over. Maybe if I have time, I can say a few more words about this at the end. All right, so this is motivation. Let's start then by formulating the problem in a more or less mathematically rigorous way, or at least tell you what are the words that mathematicians say when they talk about this problem. What is the problem? I will be, again, this is a high energy theory school, so maybe this is too easy in a sense for you. I will be just talking about general relativity, the theory of general relativity. For most of the time, I will stick to 4 dimensions, 4 bulk dimensions. So nothing weird. I will even, for most part, remove all matter contributions. So I will talk about vacuum solutions to the Einstein equations. And I will consider the problem both in the Lorentzian and in the Euclidean setting. Okay, so this is the idea. Again, this is the same that you will learn in your first course in general relativity. And maybe not in your first course, but in the second, you will learn about the problem as a dynamical evolution problem. So in the absence of boundaries, we know that the theory of general relativity can be formulated as an initial value problem. as famously proven by Choquet-Bruhat and Herog in the 50s and 60s. And the idea is that you just consider some full Cauchy slice of your spacetime. In there, you specify some initial data that I will call Gij and Kij. So I and j indices will be space-like indices. This is the metric. This is the extrinsic curvature on this Cauchy slice. And what these people showed is that out of all the Einstein's equations, there are some equations that are dynamical and will evolve this Cauchy slice into the bulk. And there are some others that are constrained. So they are first order equations on sigma. And so a first thing in order for this problem to make sense is that you need to satisfy the Einstein constraint equation here at sigma. Okay, so if you project the Einstein equation into sigma, you will have some equations. And in order for this initial value problem to make sense, you need Gij and Kij to satisfy these constraint equations. I will not write those down because they will appear again in the context of the time-like boundary, and then we will analyze them a bit more careful. But just as a start, this is what happens. And what these people proved is that basically up to some Cauchy development of this Cauchy slice, there's a unique, smooth solution that satisfies the Einstein equations and obey this initial data. Yes.
So this is saying one vacuum solution never generate a black hole?
No, so black holes will be generated. So there are a few caveats on this thing. So these proofs first are local in time. So you actually develop this for very short times, and then black holes will form, but the singularities will be formed outside this triangle here.
But if I imagine that all the time slides,
Yes.
wouldn't this be all the future cone?
All the future cone of the Penrose.
I'm thinking about the robot.
I think this thing over here will be this thing over here. Maybe not. Yeah, I think so. Your Cauchy slice will be something like this. And then this part over here will be this one over here.
If you take a maximum extended black hole, you take the initial time slice, which covers both sides. And in the future of that time slice,
Yes, that's true. But then the only thing you will be able to the only thing that you will uniquely be able to predict from this initial value sense is just up to the two horizons.
No, you would reach singularity. The singularity would be before you reach the tip of that cone.
Let's see.
I'm thinking about the initial value surface that covers both sides of the maximum extended black hole.
Like the wormhole. But
Yeah,
both will develop independently.
You fix initial conditions there, and then you evolve to the future, and the singularity lies before the tip of the cone.
Okay, let's think about. Yeah.
It was an innocent question.
Yep. Other questions? Okay, and then what we would like to do is to do something similar to what we do in ADS. That is to put a boundary. So now we will cut our Cauchy slice at some finite size, and then now on top of having our sigma slice, we will have a lambda. Is this lambda? Yeah. A gamma. Sorry, a gamma time-like boundary where my space will end. And now I will try to impose the same type of boundary conditions of initial data that I was using in the initial value problem. But it's kind of obvious that I will need to impose some kind of boundary conditions here on gamma in order to have one solution of the Einstein's equations inside. Okay, because here I will only be able to evolve up to my Cauchy horizon. And so I will have to put some boundary conditions here at gamma. And so then this problem becomes what mathematicians call an initial boundary value problem. And the funny thing is that even though these things started in the 50s, these things are being just starting to be developed a few years ago. The only one from which we have a nice result is the ADS boundary. So asymptotically ADS spaces are proven to be well posed by Frederick in the 90s. It's still 40 years from Heroj and Choquet-Bruhat. And these finite boundaries, time-like boundaries, are just now, at least formally at the mathematical level, to be analyzed.
Math question is, what conditions are the boundaries such that you have?
Yeah, I will write the exact mathematical question in a second, but just wait 5 minutes. And just for completeness, and because then it will appear, this is the Lorentzian problem. The Euclidean problem instead is not an evolution problem, but it's an infilling problem, where so let's call it infilling problem. This is sometimes also called a boundary value problem. There's no initial slice, and instead we put some boundary conditions on some boundary that sometimes, when we like to think about thermodynamics, the topology is something like S1 cross S2. And then we ask what types of solutions can fill the Euclidean space such that they are smooth in the interior. Okay? So this for us is just taking t to I tau, but for mathematicians, this problem is hyperbolic, this problem is elliptic, and those are two completely different worlds in the PDE's world, and much more is known about this problem than of this one. Okay? And I will try to give some references throughout. Yes?
One question. Perhaps you said, and I thought, in the first case, without space boundaries,
yes,
the classical problem, are there constraints on the GIJ or the KIJ that I...
Yes, they need to satisfy the Einstein constraint.
Thank you.
I will be more specific in a second. I'm just going slow. Yes. That prove this. So well, okay. So the problem is, so this is back to work by York and Gibbons and Hawking in the physics way. Is the 70s and 80s. Gibbons and Hawking is 77. The proofs of these things go back to work by... So the first thing that people proved is that the Dirichlet boundary conditions do not make sense in this Euclidean problem. That was some work by Abramidi and Esposito.
Apart from putting the Gibbons-Hawking term in the action.
Yeah. So one thing is the gravitational action to be stationary under certain boundary conditions. Another thing is for the problem to be mathematically well posed. These two things are different, and I will talk about both in a second. Right now, you forget about the action. It's just the question about PDEs. Whether the Einstein equation, in the presence of a finite compact boundary, has solutions that fill smoothly the interior of space. And that problem for Dirichlet boundary conditions is not well posed. That's what York was doing, and then we can compare what was he doing wrong and what was he doing right. But generically, that problem is not well posed, and that was noticed by Abramidi and Esposito, I guess, in the probably 90s, and then was maybe properly proven by Anderson in 2008, I think.
Say generically, you mean to be as well?
I will talk about generically in a second.
in the Euclidean problem,
Yes.
you are going to give information in the mouth of the cigar, and are you going to demand some sort of
regularity of the manifold? Yes, regularity in the interior, nothing more than that. Yeah. Other questions? All right. So I guess you are predicting what's coming. This problem seems to be well posed. So yeah. So what do I mean by well posed? Maybe it's a good time to talk about that. Well posedness. This you can go to Wikipedia and look at the article. It's quite good. It will tell you the same that I'm going to tell you now. The first requirement for a problem or an IVP problem to be well posed is the existence of solutions. And then you will see that this means existence of solutions for generic initial or boundary data. Okay? Solutions mean smooth solutions in the interior. Yes. So the first thing you need is that if you put whatever boundary data that you can imagine, and that means generic, then you need to be able to show that there will be a solution in the interior that will satisfy the Einstein equation.
Are they infinity?
That will come. There will be different versions of well posedness depending on. There are different classes of initial and boundary data and different spaces under which these things can be well posed in some sense and ill posed in some other sense. We will not talk too much about that because I don't know about that, but yes. Okay, once you stated that there exist solutions, then the next thing to show is that these solutions are unique. Uniqueness of solutions. And here the caveat is that there can be multiple solutions, like in the black hole case, where you have a large black hole, a small black hole, and the flat or the thermal gas. But these solutions are isolated. So around a particular solution, there shouldn't be in the space, whatever that means, in the space of solutions, there should not be a solution that is infinitesimally close to any other solution. Okay, so in that sense, the solutions are unique. And last, important one, is something that, I mean, the first two ones are quite obvious in a sense. You are trying to solve a problem. It better be that when you put boundary conditions, you find the solution to the problem. And if you like some kind of predictability of the theory, you want that solution to be unique. This one is a little bit different, and it was proposed by Hadamard, and is the continuous dependence of solutions with respect to the initial data. Okay, so what does this mean? It means that somehow this will be my space of solutions. This will be my space of initial data. And now I established from 1 and 2 that for a set of given generic initial data, I do find a unique solution. So this should be mapped to some point in here, and this other point should map to some other point in here. And what this Hadamard criterion is telling us is that if I move infinitesimally away from this point, I should find a solution that is very close in solution space to the previous, from the previous solution. Again, as Pedro was asking, there will be different senses in which this criterion is satisfied depending on the norms in these two spaces that you can define. And some problems can be ill-defined in one sense and well-defined in some other. So whenever a problem is ill-defined, then you try to find a rule or a measure that is less restrictive, such that if you restrict yourself to initial data with such norm, then these things are better behaved. Yeah. Yes. Yes.
This uniqueness,
Yes.
you are thinking about the initial value problem without boundary.
This is both for the initial boundary value problem that, as it is for the initial value problem.
So how do you, I don't know if this is related to this, maybe I make a large TFO and I get another solution.
Yeah, we will talk about that in a sense. So there will be large diffeos that will fail to show uniqueness, and there will be large diffeos that will be allowed, and that will depend on the initial data. These large diffeos will be large boundary diffeos, and it depends whether those can be created from the same or not the same initial data, whether they will make uniqueness fail or not. I will be much more explicit later. Yes.
I don't know this happens to realize the following. Gravity is not chaotic.
Yeah, so all these again. Yes. Local in time. So there are different scales in the problem. This is about the very beginning of the time of the dynamic evolution. Then you will have a different scale, that is that there will be chaotic systems in which these two nearby trajectories will be able to diverge, but the scales in which that happen are very different to the things that people prove in these types of theorems. Here is you look very, very close to your initial slice, and you see whether you can find the solution. So that's what mathematicians call well-posed, the local in time well-posedness. Yeah.
These local in time makes sense, but the existence of solutions for not just chaoticness, not just the third condition, but the first one, doesn't seem very physical in the sense that we're used to nonlinear hyperbolic systems that all look like shock waves.
I will talk about the shock wave in a second. But yes, so yes. Well, I don't know whether it's a question or a comment, but it's I mean, this is what mathematicians will call a local in time well-posed problem, and then there are all kinds. Then we are physicists, so we need to decide which of these things are reasonable for our physical phenomena to be described, and sometimes we will need to make our conditions a little bit softer than what mathematicians would like to do. And in particular, in gravity, one thing that will appear very soon, and that I guess in a high energy theory audience is very well expected, is that GR will not be a valid theory of gravity at the very high energy scales. And so in principle, we should view gravity as an effective field theory that describes the low energy behavior. And so if these things fail at very high temperatures, very high energies, sorry, what does it mean for us? Is it that bad, or like we as high energy physicists can live with that? Mathematicians will struggle a little more. And in fact, last week I was in a workshop in Stony Brook about this, where we had mathematicians working on this problem and physicists, and there was this clash of ideas all the time, because they were saying, oh, this problem is ill posed, we throw it away, and we were saying, oh, but why are we like this? This makes sense for us. So can't we have a, a physicist version of well-posedness that will allow for these things and still be reasonable enough to rule out some boundary conditions but allow us to use others. So, yeah. Okay, good questions. And okay, and then now the question becomes, in gravity, what are the type of boundary conditions that we can impose here in gamma such that we satisfy all or some of these criteria? Okay? And the interesting thing about all of this, and that's how I got into this problem, is that there was a theorem, 2021, by Sean-Han An and Michael Anderson, at the time both at Stony Brook. Now An is faculty in China, where they established that the initial boundary value problem in GR is not well posed, both for Dirichlet and Neumann boundary conditions. Okay? So I will try to describe in a physics language what do I mean by this, but they showed that if you impose Dirichlet boundary conditions, again, we are talking about the Lorentzian initial boundary value problem. We put initial data, Gij, Kij, such that they satisfy the constraint at sigma, and then we impose Dirichlet boundary conditions where we fix the whole induced metric at the boundary. Here for boundary indices, I will write M and N. And so GMN at the boundary is fixed. What they show is that generically you fail to find solutions in the tube for some generic GMN. And this is even worse because once you found the solution, say that you have a piece of empty Minkowski space and you look at some foliation and you look at the induced metric in that slice and you put that as a boundary data, then you do find the solution. So here the generic is very important. But once you find the solution, then they also proved that that solution in the presence of the boundary is not unique anymore. Okay? So that was kind of shocking for me when I first read that, because from these types of experiments, we are very used in the context of holography and ADS-CFT to put boundaries at finite cutoff, impose, or we say we impose some Dirichlet data, and then we do all our calculations and we are fine with it. So what's going on? Okay, so that's what I would like to discuss now. Are there questions?
No question.
Yeah.
Is there an analog of this theorem for Euclidean?
Yes. So in Euclidean, what people, okay, then again, it depends. Mathematicians will distinguish the ellipticity of the problem with the well-posedness of the problem. But these people, Abramidi and Esposito and Anderson before, they showed that the Dirichlet problem generically is not well-posed. There's lack of ellipticity, and the same thing of non-uniqueness happens in the Euclidean Dirichlet problem. And again, I'm stepping ahead because I'm going slow, but the reason why these things work is because for particular classes of solutions, the problem, both in Euclidean and Lorentzian, can be better behaved. It will still be ill-posed for mathematicians, but some things like uniqueness will be restored for particular classes of solutions. So if you have particular symmetries or you have your boundary data obeys certain properties, then if you restrict yourself to those classes of solutions, then the problem is better behaved. And one of those classes are spherical boundaries in this context.
May I ask another question?
Yes.
Maybe it's stepping ahead, but does it improve if instead of fixing the metric at the boundary, you fix a conformal structure?
Yeah, that's what we are going to discuss next. This theorem, as we will see, it was proven for vanishing cosmological constant, but that will not matter here because everything we will be discussing will happen in a very small region of space, and in that limit we will not be able to see the cosmological constant, so it will actually be more general.
And the fact that we have a small and large black hole when we use the cutoff.
Yes.
Is that like a symptom of this?
No, because those solutions are isolated solutions. So here the problems are if you find a solution, whether in your solution space, very close to that solution, there's another solution. We will see very explicitly with an example in linearized gravity how these things work and what's the non-uniqueness I'm talking about. But it will be bad. There will be a one-parameter family of solutions. If you find a solution, then there will be a one-parameter family of solutions that will satisfy the same initial and boundary data. Yeah.
Why is important the uniqueness?
For the path okay, so again, now we are switching in between Euclidean and Lorentzian things. In the Lorentzian problem, it's quite clear that if you don't have uniqueness of solutions, you are looking this as an evolution problem, right? And if you try to evolve your solution and you have multiple solutions, it's non-predictive. Yeah. In the Euclidean problem, what will happen is that we will usually be looking at the saddle point approximation, where the Euclidean path integral will localize to semi-classical solutions. And then there, in principle, the rule is that in the saddle point, we should sum over all saddles. And if you have infinite many saddles to sum over, that thing might not be exchangeable with the order of limits. The saddle point, if you have infinite saddles, you should be very, very careful on what you are doing there.
You have to impose uniqueness. It might happen that not imposing uniqueness makes a problem later. Because in principle, you might have multiple solutions.
In principle, yes. In practice, what will happen is that basically the saddle that you are choosing is a very unstable saddle because around it you will have many, many, many solutions. And this saddle point that you are computing will be highly unstable. Yes.
In this theorem, the boundary is like this portion which is light, which is the precise definition.
I will talk about this, but there will be a space-like slice that is sigma, that is space-like. There will be gamma, that is time-like. And there will be a corner. I don't know if you are asking about that, but the corner will play an important role here. There will be C, that is the intersection between gamma and sigma, where we will need to impose some kind of compatibility conditions between the boundary and the initial data, such that all this makes sense. And this corner will be important, and the compatibility condition will be important, as Philip was saying. Even if you study the wave equation and you don't impose the right compatibility conditions, you can create shock waves that evolve in the null direction. Yeah. Yeah.
Here, because you have two different kinds of PDEs.
Yes.
Can it happen that the initial value problem is well posed in the Lorentzian case? So you have predictability, but in the Euclidean still it's not well posed.
Yeah. So these are two different problems, and mathematicians that know about one might not know about the other one. And in principle, it can happen. As I was saying, this problem is known to be non-elliptic since 2008. But this problem for Dirichlet, but this problem was only proven to be not well posed in 2021. during all those 13 years or so, it could have happened that this one was well posed and the other one. What usually happens is that people first prove things about the Euclidean problem and then they prove the same about the Lorentzian problem, but that's not guaranteed from the PDEs and from the dynamical. It's a very different problem, right? Here you also need to take care about this corner that doesn't appear in the elliptic problem, so it's a much more intricate problem. We as physicists, we expect that if one makes sense, the other one also. But I will see if I get there, but we will see interesting phenomena that happens in one signature and we don't have the analog in the other one, for instance. There is some kind of law that whenever you find the thermal instability Euclidean signature, then you should find a dynamical instability in the Lorentzian theory, but that's not a theorem. That's more a physics intuition, and we have some examples where that happened. But and in the presence of boundaries, all this needs to be revisited because boundaries can carry with them their own boundary dynamics and boundary degrees of freedom, and our usual reasoning and way of thinking needs to be reevaluated.
Another question that I think, but I'm a bit confused about the uniqueness.
Yes.
Because you can do this, right? So what you mean about uniqueness, then you have different classes of solutions that are not connected by features. So
Let's discuss that in 15 minutes or so. Yes. 15 minutos. What? Wasn't it an hour and a half? Okay. Okay. I was planning on doing a simple example of a wave equation and then going to gravity. Just directly to the gravity problem. And just to compare the scalar field, this doesn't. So the scalar field theory problem, the gauge theory problem, and the Young-Mills problem are known to be well posed with Dirichlet boundary conditions. So this is something very special that happens to gravity. It's not the best. But so in total, I have 3 hours, or I have, is it 2 lectures? 2 hours and a half. Ah, okay. I prepare for 3. What am I going to do? Okay, let's discuss existence. Hopefully, this one will be shorter than the uniqueness. And here we need to start talking about the Einstein constraint equations. And so one thing that will happen in this problem is that it's not just that we will not be able to find the solution inside our world tube. It's just the solution will fail to exist very close to the boundary. So I will not be able to generically satisfy the Hamiltonian constraint equation at gamma, or the equivalent of the Hamiltonian constraint. So let me write that down. The projection of the Einstein equations in the perpendicular direction to the boundary, that's in the space-like setup, is called the Hamiltonian constraint, is given by something like the Ricci scalar of the boundary metric minus the trace of the extrinsic curvature squared. I always put the signs wrong here because I always copy the space-like, but I should put the time-like. I think now the signs will be correct. The contraction of the extrinsic curvature with itself, this thing should be 0 at the boundary. Okay, this is sometimes called the Hamiltonian constraint. And the way, what I will show in a second, or what you will have to believe me, is that I will not be able to satisfy this equation for a generic GMN that I write. Okay? So the way these people prove that is assume that you find the solution, you have a GMN, say bar, that does satisfy the constraint equation. And now let's look for a solution. Given that I need generic data, let's look at the solution a little bit away from the one I found the solution for. Okay? And let's study this equation in that regime. And so then what will happen here is that I will need to vary my 3D Ricci scalar. This will give a minus 2k delta k. And then I will have some terms that will be 2k mn delta kmn. And if you do this properly, there are some inverse metrics in here. So this will actually have one extra term that will be mr krn delta gmn. And I'm screwing up with the indices r n here. Okay? And now, if you have enough intuition, you should look at this thing and say, this will not be generically satisfied by a generic delta GMN. If you have less intuition, like myself, or like these mathematicians, what you will do is to look at the solution very close to this corner. This is called the standard Minkowski problem corner. And in this corner, what will happen is that KMN, the bar KM, this will look locally like flat. And so KMN will be equal to K and will be equal to 0. Okay? And this will mean that all these three terms will be subleading in this equation, will be almost 0 up to corrections that will come from curvature. And so you end up with some equation that is telling you that the 3D Ricci, or the variation of the 3D Ricci scalar, has to be 0 at the boundary. And this is very non-generic. If you just put any variation of GMN, you compute the Ricci, and you will not find that this linearized Ricci thing will be 0. Okay? So that means that if you are trying to find the solution that is a solution to the Einstein's equations in the whole world tube, you put some boundary data, and you can already fail to solve these equations at the boundary, very close to this corner.
But this really doesn't sound surprising because you have the constraint. You have the Hamiltonian constraint.
Exactly.
And of course, you won't satisfy this constraint with an arbitrary perturbation.
Exactly.
Yes. It has to satisfy some condition.
That's exactly the reasoning, and that's completely true. The only difference is a little bit about interpretation. So when we talk about initial data, we talk about the phase space of solutions, and we are somehow happy with restricting from the whole phase space of solutions to those in the phase space that satisfy the Einstein constraint. Here, we are talking about boundary data that we want to interpret more as boundary data, like theory data. So we don't want, in some sense, to restrict the space of it. It comes with the theory itself. This data, it doesn't come from the solutions. So in a sense, that's the difference. It's totally true that this is completely expectable if you did the initial value problem. You know that you need to in order to satisfy the constraint, you will need to put Gij and Kij in a very particular way. What will not be that obvious is that when you do find the solution, uniqueness fails badly. Yes.
So, ignorant question, but in addition to GMN, isn't KMN independent data? In other words,
In principle, is okay. You can ask about the number of data that you need to impose, and that's the number of data of a symmetric 3D tensor. So it's 6. So in principle, the number of independent free data that you will need to impose in order for the problem to be a solution. It's the number of data that is here in GMN. It's true that KMN is also free in principle. So in the space-like slice, what you do is you put both, but then you impose the constraint and you restrict the number of final data.
So maybe another way of asking this is, for given GMN, does there exist a KMN which satisfies?
Yes, there will be data that will satisfy the constraint, yes. But that will not be a generic boundary data. So you can try to do this problem in a different way. That is, I will do Gij, Kij in the initial slice, and I will do GMN, KMN such that they satisfy the constraint in the boundary as well. And that's another way of doing the problem. You can do that problem in that way. The problem is the interpretation of what you are doing in terms of boundary conditions.
Forget general relativity.
Yes.
Just have a wave equation. And
Yes.
then I'm used to, on the initial slice, put in initial data and time derivatives. And on the boundaries, just data,
Dirichlet.
but not the normal derivatives.
Yes.
Because then I'm overspecifying.
Yes.
Is this the same thing?
Yeah. I was planning on doing the wave equation first, where I will put initial data and then the first derivative, and then only Dirichlet data at the boundary, and that's enough to solve the whole problem in the positive quadrant. Here, because there are constraints, the problem is a little bit different, but the number of data is the GMN data.
Can I make a comment?
Yes.
The criterion constraint at the non-perturbative level, it's not really a constraint on the metric at the boundary, because you have K, which is not specified at the boundary. But then when you linearize, you get a constraint which is only the metric at the boundary. This is
So this is the whole point of the proof, is that you can go to this Minkowski corner and then you don't care about K, you will fail here at the corner to satisfy this thing. Again, generically.
So you're writing the Hamiltonian constant, which is one of Einstein's equations.
Yes.
And then where are you taking a
variation? I'm saying the number one criterion says that I need existence of solutions for generic initial and boundary data. Okay, so I'm saying, say that I found one solution that is this G bar. Because of this genericity thing, if I take this data, I should also be able to find the solution. And I fail.
So if you compare with the case in which there is no problem,
Mm-hmm.
one, how
I don't need to talk about corner or boundary.
you will make also the variation. You can make the variation, but you will not get this restricted condition.
Yeah. So here
the variation and the A is not zero.
Yeah. So in this problem, I do a different type of thing. That is, I specify Gij and Kij, and I imposing on top of that they both need to satisfy this equation. Here I'm saying if I just specify GMN, I will generically fail to do that. And the difference, why I do this here and why I do this here, is that here I'm taking this as an initial value problem where these things are parameterizing the phase space of solutions. While here I want to take this data as theory data that comes already with the theory. I don't want to restrict the set of parameters that I can use in my theory. It's like saying that I will have Einstein with a cosmological constant, but I don't want lambda to be 34, but I allow it to be 35. Okay, how much time do I have? 2? Okay, I wanted to do the uniqueness problem in detail because many people ask about diffeos and how this thing. So again, okay, so let me just do a quick summary and then we can continue in the next lecture. So far, we are trying to understand what these people, Ann and Anderson, were telling us, that is that the initial boundary value problem in GR is not well posed when we impose Dirichlet boundary conditions, which mean that we are fixing the induced metric at the boundary of my world tube. And they showed that this fails both in 1 and 2, both in existence and uniqueness. We don't even need to talk about Hadamard, because if there's no one-to-one map between these two, there's no reason to discuss continuous dependence. And I was trying to argue now that the existence problem fails because generically we will not be able to satisfy the Einstein constraints equations when we impose Dirichlet data at the boundary. Okay? And the next time, the next lecture, what I will show is that even if you do find a solution, again, the typical example is I start with Minkowski space, I look at the constant x slice, I put eta mn as boundary data. Of course, that's a solution to my initial boundary value problem with trivial initial data. Then what I will show is that on top of that solution, there will be infinitely many more. They will take the form of locally diffeomorphisms, and I will show you that independently of your initial data, that all these diffeos will satisfy your initial data, and so they should be considered as physical solutions of the same initial boundary value problem. Okay? And if I manage to do that in the next lecture, then I will tell you that in this same paper where Aaron Anderson proved this theorem, they also conjecture that there are a set of boundary data that are called conformal boundary conditions that are much better posed. And as far as we know, at least they satisfy, or they are close to satisfying existence and uniqueness, even at the nonlinear level. So with that, I'll stop. Thanks.